because the mix of particular colors you have to do, it's not a linear thing. So it's kind of done as a lookup table. So, and then in the end, it turned out nobody was willing to pay the price to add that kind of sophistication to their bulb. And they just accepted the fact that the color temperature wasn't going to change. One of the things about, you notice when we get back to our color chart, it takes 3 colors to define a color space. With 2 colors, the only thing you can get is something between the 2 colors. If you have 3 colors, it defines a triangle. You have access to anything inside that triangle, which is a good thing. It means you can, by adjusting the mix of particular colors, you can shift the color of the bulb. That was a big deal when we were doing projectors, because arc lamps, kind of by their nature, are very deficient in red light. They have plenty of blue and green light, but they don't have much red light. So we would have to do things that would sacrifice, oh, thank you, that would sacrifice light output for the sake of getting a better color rendering. So if you've ever had a projector and it has like a cinema mode or a movie mode, in that case, you'll notice that the output is less than in, let's say, office mode. And that's because they've had to reduce the blue and green output to kind of bring up the red. So that's one of those things you kind of sacrifice with when you have a bulb that only puts out so much light in every spectrum. Your only choice if you want to bring up one is to throw away the others. So, okay, so a couple of things you'll notice here. You'll notice along the outside is some numbers. They're going from, let's say, 380 all the way around to 700. Well, those are wavelengths in nanometers. And those are the perfectly saturated colors through the spectrum. So when we talk about color saturation, that means that the spectrum of that particular color is extremely narrow. Okay. As you start to get to the inside, you start to get a mix of colors. And when that happens, the spectrum kind of spreads out. So now you get basically any color you want inside. If you have access to every point, you may not. So the colors around the edge are 100% saturated colors. Now the line at the bottom is called the line of purples. It goes between red and blue. So anything on that line kind of goes from deeper purple to red to blue. So, questions about that? It's a pretty interesting curve. So you'll notice the black body curve is not a straight line. In fact, I've seen the equation for it. It's not exactly parabolic, although it looks a lot like it's parabolic. So when I was trying to mix 2 colors to give it some level of color shift, you really can't do it with 2 colors. Like I said, the best you can do with 2 colors is somewhere in between. With 3 colors, you have a better color space. Okay. The black body curve is also called the Planckian loci, and it defines white. These are kind of the things I just talked to you about. So here's a color space defined by this triangle. So if you have 3 sources, you have access to anything inside that triangle. If you want to expand your triangle, you're going to have to add some sources. And that's one way to do it. Maybe you want a deeper green or more red or more blue. You're going to have to move your source away. Now, ideally, all your sources would be on the perfectly saturated perimeter of that, but they don't have to be. If you look up the specifications for any given LED, the manufacturers are pretty good about giving you what their spectrum is. And it's usually reasonably broad, not super broad, but I mean, it has a predominant peak, and they'll talk about what's the predominant peak. Also, when you look at that, it's normalized data. So the predominant peak is at 1 or 100%, and everything is referenced from that point. So this is what projector manufacturers play with, the color spectrum. Now this one's very interesting because it gives you a view of not only the color temperature, but the color rendering index. And these are spectra of particular sources. Now, the most interesting one, I think, is the one that's called sunlight. The sun is a very broadband radiator. It's got a lot of colors in it. It's very rich. Now, you'll notice as we start to look at, you see the blue spike in 2 of them, okay? Those would be either an arc discharge type of lamp because they're very rich in blue light, or it could be an LED in there that has a spike in the blue. And you can see that the broader the spectrum, the better the color rendering is. So if we go down to the last one, you notice that it's not very broad. It's got a peak somewhere in the neighborhood of 555 nanometers. And you can see it has the poorest color rendering. So we would call this cool light or 3500 Kelvin. And because it's not rich in all of the colors, it has very poor color rendering index. And you can see that as the color rendering index gets better, it tends to fill out the spectrum better. Now, incandescent bulbs have a pretty broad spectrum. They're broad radiators. They don't make light like LEDs or fluorescent bulbs where they're making spikes in particular colors. It's fairly broadband like sunlight. So if you want something that renders color really well, you're going to want, like, if you can't have sunlight, incandescent bulb is the way to go, because it's going to render all your colors pretty well. Now, the one kind of bulb I did not bring up, you've heard of halogen bulbs. Okay, that kind of was not a variation, but it was an upgrade to the traditional tungsten bulb. So the wear out mechanism for these bulbs is tungsten evaporation. As the bulb ages, the tungsten evaporates, the tungsten being the hottest thing in the bulb, and tungsten always goes to the coolest place in the bulb, which is the bulb wall. So over the life of the bulb, the tungsten evaporates and gets deposited on the wall of the bulb. So it was determined that if they added some halides to the bulb, they would get this scrubbing action where we scrub the tungsten off the wall and redeposit it back on the filament. They would also be able to run the bulb much hotter to make the halogen cycle work. Because if you dim a halogen bulb, it'll fall out of its halogen cycle and you don't get that scrubbing action. So they had to run them hotter. Now, it's not perfect. It's not like it's continuously rebuilding the filament so it'll last forever, because you don't exactly know where tungsten is evaporating in the bulb. Typically, the worst place is in the middle of the bulb. And eventually that filament's going to wear out anyway, even if it's a halogen bulb. But they do last longer, and they were kind of an upgrade for these. And they haven't been all outlawed yet. I don't know if you've tried to look for an incandescent bulb lately, but if you go to your hardware store, you're hard pressed to find them. Now, there's certain applications they work really well in, okay? Like your oven, the oven light, okay? If you put an LED in your oven, you would just have a puddle of goo in there, okay? These bulbs work really well because the filament is already running you know, 2,700 Kelvin. So putting it in the oven doesn't really heat it up that much. So, yeah, there's still some specialty applications where incandescent bulbs are really good, and they won't be replaced with any other technology. Okay, now here's one that's particularly telling. Now you notice that the spikes in the fluorescent lamp, you see a lot of spikes, not a lot of broadband activity. We would call these narrow band spikes because, well, they have a very narrow spectrum. While when we get out here into the incandescent bulb, you start to see that you have a very broad spectrum. And it goes from red to blue. Now, because of the nature of the incandescent bulbs, they naturally have more red in them than blue. Okay, but it's not zero. But it does tend to be on the red, yellow, orange scale. While fluorescent bulbs, these would be blue and red and deeper red. And getting into the infrared scale. So it turns out that mercury lamps tend to be very rich in blue-green light and very deficient in red light. Okay, so here you can get LEDs in different colors, and this gives you an idea of the spectrum based on, let's say, the correlated color temperature. So the warm white one, which is the yellow, you see it doesn't have a lot in the blue, tends to have a lot more in the green. Let's see. Of course, you have discrete colors. Cool white tends to have more in the green and blue, not so much in the red. But regardless, LEDs are going to have peaks in them. That's just the way they work. Incandescents have a very broad spectrum, which is why they have very good color rendering index. Okay, before we go on to key characteristics, any questions about what I talked about so far? Yes, sir.
So, I noticed in the graph, and when you just said how LEDs only have, they just have a lot of peaks. I guess I don't understand how, like where I see comment like my friend did like LED that you change colors to whatever.
How does that work?
Yeah.
Okay, LEDs can't change colors. What they have is different color LEDs.
Oh, okay.
So inside the bulb, they have a discrete red and a discrete blue, and let's say a discrete green. And the way they make white light is they go, okay, so white light is roughly 69% green, 21% red, and the rest is blue. Okay, but you can change those mixes. So they're not actually changing the light output of any particular LED. They're just turning some on and turning some off. So, yes, sir.
Seeing for instance, we're seeing the round fluorescent bulb that was more of a kind of more reddish tint. They just make up a brighter one of a blackout with which
it depends on the phosphors they put in the bulb. So the phosphor is when they make the tube, they actually fill it with phosphor and then they drain it back out, and then they drive off the carrier. So the phosphor kind of stays on the wall of the lamp. And depending on what kind of phosphors they put in it will determine its color characteristics. So all the phosphors are sensitive to 254 nanometer UV light. And that's one of the big spikes in the mercury lamps. Also 185, but that's not very useful for making light. It's actually kind of detrimental to the life of the bulb. So that answer your question? Okay, key characteristics. Now this is an interesting slide. I wanted to put this together to kind of give you the pros and cons of any particular light source. Now, you'll notice the incandescent's got a lot of pros, right? It's low cost, or it used to be low cost. The price is going up now. Lumen maintenance is excellent. They are really good right up till they die. Ambient temperature because they operate at such a high temperature anyway, they're pretty insensitive to the environment. Life, not so good. Couple thousand hours tops. Now, if you reduce the voltage on your incandescent bulbs, you can make them last longer. So it's an extremely strong function of voltage, which means it's an extremely strong function of temperature. So the higher you run the temperature, the faster you're going to boil off that tungsten. But if you reduce the voltage on your incandescent lamps, they could easily last 10 times longer than their average rated life. But that also means you're putting out less light. Color rendering, really good. Color, correct correlated color temperature, it's going to land in that 2200 to 2700 Kelvin range. You can't run it much hotter than that. If you do, you're going to shorten its life by quite a bit. So everybody been on a plane, right? So you ever seen the landing lights on a plane? Okay, so those are 600-watt landing lights. They have a rated life of about 100 hours. So every 100 hours on average, they have to replace one of those. So the less they use them, the longer they're going to last. Now, I worked for an aerospace company and we had to design transformers for these things. So the problem is, it's also, you can't take off your plane if you have a landing light out. So it's a dispatch item. So, but some pilots will actually keep the landing lights on in flight. So life is, when I say 2,000 hours, I'm talking about bulbs like this. Some other specialty bulbs are much, much lower. Okay, flicker, very good. It's about 10% with these. The chances are you probably won't notice that. Now we get into the bad side. Voltage sensitivity is very high. It's something like a 12th power of the voltage above its normal rating. So if you run the voltage up much, you're going to shorten the life quite a bit. On the flip side, if you lower the voltage, you're going to increase the life quite a bit. Efficacy, 10 to 25 lumens per watt. They're pretty pitiful. Okay. Now, just as a general rule on that, how do I know it's pitiful? Even if I didn't know anything about the efficacy, they get really hot. Okay. They're really good at turning electricity into heat. Not so much about turning it into light. Color, turn on, turn off time, they're slow. It's noticeable. They have to ramp up because it has to heat the filament up, and that takes enough time to notice, which means it's in the 100 to 200 millisecond range. And when you turn them off, they don't immediately go out, they kind of decay out. On automobiles, if you see a turn signal and it's very abrupt, that's a dead giveaway, it's an LED. The old incandescent bulbs were kind of soft turn on and soft turn off. Variable color, nope. You kind of get what you get. That's just the way they are. Now, fluorescent lamps, we're approaching the 100th anniversary of fluorescent lamps. Cost, they're medium. Okay, you can't plug them directly into the wall. They require some kind of a control mechanism, something we call a ballast. And it does that because it has to give enough voltage to get it started, and then it has to limit the current. So every fluorescent lamp requires a ballast. Lumen maintenance, it's not bad. It's not as good as a fluorescent or incandescent. So over life, you might lose 20 to 30%. That's not too horrible. Sensitive to ambient temperature. They're very sensitive to ambient temperature, more so for cold temperatures than hot temperatures. So once you get below about 50 degrees F, the drop off in light output is very noticeable. And by the time you get to 32 F or 0 C, you've lost 90% of your light. So it's very heavy drop off when they get cold. Now it drops off when they get warm as well, but not nearly as bad, maybe not even noticeable. Optimum temperature for fluorescence is around 77 F. That's kind of where they work best. Color rendering, it's got spikes. Color rendering is not that great for fluorescence. Correlated color temperature or color rendering is poor. Correlated color temperature depends on the phosphors they put on. It can be very broad. You can have, call it a warm white. You can also have daylight, which is 5,000 plus. Flicker, very high. Most fluorescent lights have a lot of flicker. Some people are more sensitive to it than others. Voltage sensitivity, not too bad because it's got a control mechanism that mitigates a lot of that. There's one I forgot to mention, shock and vibration. Because you've got a small filament here, they're not real good for shock and vibration. In fact, the bulbs that, if you need an incandescent bulb and you need good shock and vibration performance, you're going to get a low voltage bulb. And the reason for that is the low voltage bulbs have a heavier filament in them. They're stronger, they're stiffer. These bulbs won't take much at all. You drop them, light goes out, that's it. Efficacy, fluorescents are much better than incandescents, in the neighborhood of 100 lumens per watt. That's pretty respectable. Turn on and turn off. Now I say fast, but maybe you had an experience where you turned on a fluorescent light and it took a little while to come up. That is strictly a function of the ballast. It is possible to have fluorescent bulbs come on nearly immediately. Okay, they call them instant start. Variable color. Now, I said you could get different colors, but what you can't do is change the color once it's established. So once the bulb is built, it's going to be that color. So you can choose the color you want, but once you've got it, you really can't change it. Now, LEDs, cost is coming down. You can now buy a replacement bulb for $1. Really good. Now, the price you pay with that is you'll probably have to replace them more than you wish you would. In principle, the LEDs will last a long time. Like I said, the electronics is going to die on you much sooner. Lumen maintenance is really quite good. They hang in there until they die, until the electronics dies. Ambient temperature, they're relatively stable with ambient temperature. They're really not sensitive to cold or to heat that much within limits you would want to live in. Don't put one in your oven or it'll turn into a puddle of goo on you. That's pretty high temperature. Color rendering is quite good because you can add different colors into the mix there. Flicker is really driver dependent. It depends really entirely on the electronics. The LEDs themselves don't have any inherent flicker. So if you had a really good driver, you could have very, very low flicker. That also would account for the fact that they're voltage insensitive. So the driver regulates out all the voltage changes on the line. For shock and vibration, you don't have any inherent failure mechanism like a filament. That's not to say you can't destroy them by dropping them. Just like any electronic item, if you drop it hard enough, you can break it. But they are solid state devices. Efficacy, quite good. 200 lumens per watt. And compared to an incandescent, that's about 10 times better. So to put that into perspective, so we remodeled our kitchen many years ago now. And in the kitchen, we had these, they call them GU10s. It's a particular style of bulb, and it's on a little rail that you plug them into. And if they were incandescent bulbs, they would consume about 50 watts each. So when you have 10 of them, that's 500 watts of light. So if I replace them with LED GU10 bulbs, I save more than one bulb that's incandescent. Because now it's 10 times more efficacious. So the entire consumption by the string now is equal to 50 watts. So it really does save a lot. Now, having said that, I've replaced them a lot more than I wish I did, but when you buy cheap bulbs, you get cheap bulbs. Turn on, turn off very fast. Variable color? Yes, you can have variable color. You were telling me about the variable color, you can dial it up. If you have Bluetooth, you have different LED colors in there, you can move it from one color to the other, no problem. Okay. Now, how do we drive LEDs? Now, this characteristic, it may not have much meaning here. I'll try to make sense of it for you. There are 3 different color of LEDs here, red, green, and blue. And the reason they have different characteristics has to do with the materials they're made from. And it's not inherent that red has, that it looks like that. So this axis is voltage and the vertical axis is current. Now you'll notice that once you get to a certain voltage, the current shoots up rather sharply. And it does that for all of these. So LEDs are kind of modeled as voltage sources with a series resistance. So we do not control them by controlling the voltage. We control them by controlling the current. They're current-driven devices. If you try to voltage control them, you will have, your output will be all over the place. Not only that, but the voltages that you see are going to change with temperature. As they get hot, voltage tends to come down in semiconductors. So don't try to voltage. If you're going to build a circuit or a little project, don't try to voltage control. They just won't work. Luminous intensity. Okay, we talked about that. So we know that lumens is a measure of total light output. Now you go, well, what's a good figure of merit? I'm redesigning my kitchen or my dining room, and I want to know how many lights do I need to put in? How do I figure that out? Well, a good figure of merit is 300 to 500 lumens per square meter. So if you know how big the room is, that'll give you an idea of how many lumens you need to light it up adequately. So that's pretty good. That's office environment. Maybe you want ambiance. Probably best to put a dimmer in if you want to bring the power down. But maybe you don't need it to be that way. It's always going to be dim. So you can bring that number down. But that's a good figure to have when it comes to deciding how much light you need. Okay. Now, this is something called an integrating sphere. I told you lumens can be measured, but it takes a little bit more equipment to do it. You need an integrating sphere, which is one of these. Now, you'll notice that, now this one is 1.5 meters in diameter. The inside, you notice, is white. Okay, that is barium sulfate, which is highly reflective. It is 99% reflective. So you may think of, well, I need it to be reflective. I need to have a mirror. That's not true. White is a diffuse reflector. Now, why would we put a diffuse reflector inside an integrating sphere? Because when light impinges on the barium sulfate, it tends to disperse in multiple directions. It spreads out. And after it goes through a few bounces, the detector is in the middle and it detects how much light. In fact, if you played around with one of these, if you took like a laser pointer and you pointed it in the inlet, you would find out the whole sphere glows red or green or whatever your light source is. So we use these a lot when designing projectors because that was our horsepower measurement. So that's how we compared ourselves to other vendors. How many lumens do you put out? Okay, so you need an integrating sphere to do that. Not the kind of thing you're going to have, but if you're a lab, you probably have one. Okay, Typical specifications for a bulb. So equivalent light output, maybe you've seen, you go online and you look for a bulb and they go, hey, this is 100 watt. Well, it's not 100 watts, it's misleading. Okay, what they mean is it's equivalent to a 100 watt incandescent bulb. So, and a 100 watt incandescent bulb is nominally rated at 1600 lumens. So when they say you need to read the fine print, the size of the envelope, believe it or not, the industry has established that these are very well-defined envelopes. Why did they do that? Well, they want to be interchangeable and they want to fit in a particular fixture. So they needed to standardize the mechanics of the bulb, the base and the bulb itself. So just FYI, the base here is what they would call an E26, which means it's 26 millimeters in diameter. And the bulb would, I believe this one, they would call it an A19, which defines the shape of the bulb. Okay. Color correlated temperature, they're going to say that. Lumens, they may or may not say that. Actual power consumption, that's one you're really concerned about because that's what you got to pay for. And last but not least is the dimmable versus non-dimmable. So the very first LED bulbs were not dimmable. They were not compatible with dimmers. Now, like I said, dimmers have been around since the 1960s. And the industry took a really horrible way of trying to help you make a decision about compatibility. So what would happen is the LED bulb manufacturer would test his bulb with a bunch of dimmers. And there was probably 10 or 20 that were common ones. Now, I would challenge you, who has a dimmer? Win has a dimmer. Do you know the model number of your dimmer? And therein lies the problem. Not a clue, because maybe you bought the house and the dimmer was there, right? You don't know what kind of dimmer's in the wall. And having a manufacturer that said, hey, we're good with this set of dimmers, and you go, so what? I have not got a clue about what I've got. And that's the way the industry decided to approach this. What they should have done was develop an interface spec that would say, these dimmers are going to behave like this, and these bulbs are going to behave like that. And if everybody meets the specification, it's all compatible. But they took the cheap way out, so you kind of have to guess whether the bulb is going to be compatible with your dimmer or not. Now, there are some dimmers on the market that are more friendly to LEDs than others. But again, I always called it the grandmother effect. That is, if your grandmother could do it, it's good, right? Grandma knows how to screw it. She's familiar with that mode of operation. Does she know how to put a dimmer in her wall? Probably not. Okay, does she know what dimmer's in her wall? Probably not. So saying that was kind of a brain dead idea on the industry's part. Okay, I brought this one up because it had all the relevant information. I'm not advocating for this brand, but you notice they have all the relevant information. They tell you the color temperature. They tell you that it's an A19 size, which is this. It's an E26 base, which is this, which is the most common one. They tell you that it's 1500 lumens, which means it's a 100-watt equivalent. And they'll even say that on the package and tell you, actually in bolder numbers, how many actual watts it consumes. So you get to know how much you're saving there. Now, it also says, and very clearly, that it's a non-dimmable bulb. Okay, that is kind of important. So, oh, another thing here, I always like this one. You'll notice that it is UL approved. You want to know if it's UL approved? Look up the number. Depending on where it's made, That may not be the real number. There might not be a real number. Okay, but you can look it up on the UL site and it'll tell you if it's really a UL approved bulb. Okay. Talked about this a little bit. What we call phase cut dimmers. Those are the ones we've had for years. So the way they work, the manufacturer just declares what they're compatible with. Okay, so this curve may not have a lot of meaning to you, but you'll see a lot of things up there. NEMA 6, NEMA 7. These are standards in the US for dimmers. And on this scale, it goes from 0 to 180 degrees. Now, we only look at half cycle. We know a full cycle is 360 degrees. But the way the dimmer works is it turns off the power somewhere through the cycle. And that's how we reduce the power into it. Now, you notice they kind of start around here and kind of stop around 40. So the operating range for this is about 100 degrees. So incandescent bulbs, which are the blue line, you can see the blue line, you can see that it drops off very sharply. That's very hard to copy with an LED bulb. We have to do things to make that work, and it doesn't work that good. So you'll notice that in the middle, the variability between the particular performance is huge. It could be 30 or 40% different from one manufacturer to the next. And this is what I mean by a phase cut dimmer. So the sine wave you get into your house, the dimmer will either turn on late or turn off at some time. We call this a leading edge dimmer because it delays the turn on. And the one in the back is called a trailing edge dimmer. Trailing edge dimmers are very compatible with LED lighting. Unfortunately, they cost a lot more and they're a lot more rare. They are made, however. I know I'm hurrying up, but I'm feeling like I'm getting long here. Life testing. Okay. Life testing is a well-established practice for bulb manufacturers. They use a controlled environment. They have controlled input voltage. They cycle the bulbs periodically, and there's a defined sample size for the lot. Now, they call it average lifetime. It's not really average lifetime. It's median lifetime. So what that means is they have a population of 100 lamps, let's say. So when the 51st lamp fails, test is over, and they go, that's our average life. Half of the bulbs work, half the bulbs die. That's how they define life. So it's not an arithmetic mean where they run all the bulbs to failure and then add up the operating hours and divide by the sample size. So this is really a mean or a median. But they also realize that most people don't know the difference, so they're just going to call it average life. I do think we have reached the end. Okay. I know we're out. Yes, Nick.
What is conduction?
Conduction angle. So out of your wall, you're getting a sine wave of voltage. So it's in the US at 60 hertz. So over one cycle, that would be 360 degrees, right? So the positive half and the negative half kind of have the same phase angle. So the conduction angle is how long, what percentage of that 180 degrees is conducted. Now it can be very long, up to, now it can't be 180 because you have to have some operating voltage. So that's why they go to like 140, some will go up to 160. So what they'll do is start cutting back on, they'll start delaying the turn on time. So the conduction time is the amount of time that current is flowing through the bulb. And once you get below like 40 degrees, it's pretty much off. So that technique is used for all kinds of power control devices. If you got an electric stove, you've got a phase control in there, control electric power. Now, because it's a sine wave, the average power is not linear with the phase cut. So, so when you're cutting the phase off at the where the voltage is low, you're not really reducing the power that much. So, yes. Other question? Yes. I saw Corey first.
In our circuits course.
Yeah.
That we're taking right now.
Yep.
We're learning about inductance.
Yeah.
Capacitance.
Yep.
So what, is there like an important role that those elements play in commercial, like keeping a commercial LED reliable?
Well, okay. The answer is yes. Okay, so every LED bulb in it or that has an electronic driver inside. And that circuit inevitably has some number of capacitors and inductors in there to condition the power going to the bulb. So the answer is yes, it does. But it's also a high frequency switching type converter to keep the size down. Dr. Moore.
Okay, so on one of your graphs about 4 or 5 slides ago, you were talking about it was the IV characteristics, and you had the IV characteristics for like different colors of
Yes,
or different colors of LEDs.
right.
And I noticed this because when I started doing research with optics and lighting, it was always relatively easier to get red LEDs and green LEDs than it was to get blue ones at first because of, I assume because of power consumption and the amount of voltage you would have to put through the materials that you would have to use to get the blue LEDs. But is that still the case in terms of, because it seems like with the modern LED situations, you can have pretty much all the different
Yeah.
color bulbs without too much trouble. So I
Right.
assume that
The blue was the last color to be developed. I believe it was a Japanese company that developed blue LEDs. And they were all the rage. Red has been around a long time, green has been around a long time. Blue is newer, but they're not rare or particularly that expensive anymore. So now, the one thing you can do when you drive different colors of LEDs, you can drive them in series and they'll all be driven with the same current. Now their light output is going to track roughly with their current. So it's more or less linear until you start driving them way too hard. Then when the output keeps going up, but it starts going up slower. Did that answer your question?
I think so.
You think so?
And I just remember that when
Yeah,
I was working on a project in undergrad that we were supposed to use, that we were supposed to video an experiment that was supposed to go out into the space shuttle. It never made it, but that has historical references to it. But when we did our testing, we always ended up using the blue LEDs, but part of that was because the video cameras that we were using would preferentially pick up the blue light as opposed to the red or the green. So I knew we were using the blue lights for the part of that was also, but that also controlled like what our voltage regulator circuits look like compared to had to power the whole thing on a
Sure.
DC bucket for piece of ladder.
yeah. So one thing you notice, if I can see if I can back up here. Oops, no, I don't want to do that.
You want to share your screen again?
Oh yeah, there we are. Okay, so we're talking about this one. So you'll notice that just because of the difference in the semiconductor material, the voltage drop across them tends to be a little bit different. I mean, they're similar, but they're a little bit different. And that's, to get blue, you have to use different materials to get blue out of your farm wells. And red is pretty easy to get. Green, well, your eye is most sensitive to green, which is kind of good. Since our white light is largely made up of that. So just an interesting fact, we talked about lumens. So if you could convert every electrical watt into an optical watt, the conversion is 1 electrical watt would give you 683 lumens at 555 volts. So you can see 200 lumens. You go, wow, that's pretty good. It's way better than 25 lumens. Still 33% efficient in terms of power conversion from electrical watts into optical watts. So now the one device that's actually respectable is laser diodes. They're close to 50% electrical to optical watts. So
Thank you for that. That helps explain a few things, and I know given the different types of LEDs, they all have different applications, so it's more like.
right. So, you know, if you wanted to make in principle, if you wanted to make a 2000 lumen projector, that's only like 3 optical watts or a little more than that. So, I remember when I first went to work for InFocus, the guy I was working for wanted me to do an analysis from power out of the wall to light on the screen. Well, it pretty much all turns into heat, is the truth. So what comes out is a pitiful fraction of what went in. So.
That big of a fan when you turn the thing off.
Yeah, that's a dead giveaway that it's not too good, right? You know, and you know, that's kind of my what do you call it? Quick engineering analysis. If it gets hot, it's probably not very efficient.
Energy has to go somewhere.
And you know, that
exactly.
law of conservation of energy is still true. So, you know, I mean, your car is also pitifully efficient, right? So electric motors are what, 90% efficient, which is way better than the 15% your engine is, but there's a lot more energy in a pound of gasoline than a pound of batteries. So yeah, there's that.
Yeah, and then of course you have things that even when they are running in peak efficiency, you're still looking at peak efficiency for certain things might only be like 30 or 40%. So
That's true.
You're still losing like two-thirds of your energy into things you can't really use it for.
That's right. Yeah.
You'd love to be able to recoup that, but logistically it's not.
Yeah.
Once it turns into heat, it's gone.
Yeah, it's kind of gone. So that's a true statement. Very good. Any other questions? All right, I guess we're done.
Thank you
You're
very
welcome.
much,
You're welcome.
Frazier, for that.
My pleasure.
For those that unfortunately ended up joining the live stream due to technical difficulties, please see our SWOCC team pathways page and and we'll have a number of different announcements within the SWOCC community talking about events upcoming. Our next major event, which Cassie discussed earlier, was we're doing a joint thing with the Coos Bay Fire Station and the Coos Bay Library to go into the deep and discuss marine biology through the planetarium at the Coos Bay Fire Station on the 30th of January, and join us on the 5th of February for our Artemis II launch prep party. And I think Lynn stepped out, otherwise I'd have her introduce her, have her talk about her her next lecture, which is February 10th. We're going to have we're gonna have a paleo lecture on marine mammal fossils. More information about, that's what you like that.
If you didn't sign in and would like to sign in, feel free to do that, but I think that would be that.
I'm looking at the whole you got.
Yeah, absolutely.
Okay. Right. Yeah. Right, but the compact ones, I don't know, as they want to usually replace again. That's what they're doing. And they did the best they could, but there are a lot of places. And they also require their electrical exceeding the cheap.
Oh, yeah, that absolutely. Of course not.
There's not, there's all kinds of things that we can say about, our side of the world too, so.
And that's fiscally improbable.
When they outlawed initially about 6 subjects there.
Things that you actively use mercury for, you do it carefully, because you've got the mercury bulb, and then you've also got the mercury barometers, which is typically.
Right.
Use those, because otherwise if you're doing a water barometer, it makes the thing have to be 13 times as tall.
It's all hard to read up there.
Yeah, it makes it a little harder to. It's a little harder to actually put it in the building where it has to be. Yeah.
Yeah, and we ran into that. Problem. All of those. High pressure. They run about 300 amps.
And those specifically are all protectors.
So there. There's a lot of mercury. There. Goes off, it sounds like a pill. Yes. Mercury and vapor phase.
Where you want to turn on.
Yep.
Not to mention,
Well, that's sure.